right, this presentation deals with simple harmonic motion in the terms of properties of waves and sound waves. And remember that you can always visit sciencewithmrnoon.com and you can see interactive videos, you can see presentations, PowerPoints, interactive labs that you can do, animations that allow you to do interactive stuff, and the online quizzes that help you test the knowledge that you might have obtained from these videos. So remember, just because you're watching this video doesn't mean you might not need to go to sciencewithmrnoon.com, unit on waves and sound, to learn about all the background information that goes with these problem-solving strategies. All right, so now that we got that out of the way, we will look at today's presentation. Restoring force acts to move an object back to equilibrium. We discussed this already. Simple harmonic motion. We have our restoring force. As displacement increases, so does our restoring force. So we have a direct proportionality. And when our change in displacement equals 0, our restoring force is equal to 0. So an object in equilibrium has no restoring force. And what we see is our examples of simple harmonic motion. Objects that are at equilibrium are masses on springs that are not vibrating up and down, and pendulum bobs that are at their lowest point, are at the equilibrium positions. All right. For a mass spring system, Hooke's law applies, which we discussed already, that the restoring force is equal to the spring constant times the change in displacement. And in this equation, we see this direct proportionality between our displacement and our restoring force. Energy, the ability to do work. And kinetic energy is the energy of a mass having a velocity, or an object in motion. And Ke is 1/2 mv squared. We discussed this before. We have objects with mass. When they're in motion, we have objects with velocity. When they are in equilibrium, we have no motion taking place, no motion on the pendulum bob, no motion, or very little, should be no motion on the masses on spring scales. And also when we have an object at its maximum displacement. So when I let this go, up here we have all potential energy and no kinetic energy. Here we have all kinetic energy and no potential energy. And here, once again, the object stops just before it changes direction, and we have all potential energy and no kinetic energy. So if we see this object in motion at the maximum displacements from the equilibrium position, we have all potential energy and no kinetic energy. And at the equilibrium position, we have the greatest velocity that takes place. It's the same with our objects in equilibrium right now. We have no motion. If I stretch it at its lowest point and its highest point, its velocity is changing direction. So we have 0 velocity at the lowest point and 0 velocity at the highest point. We have full elastic potential energy, and the greatest velocity that's taking place from this restoring force acceleration is at equilibrium point as it's going through equilibrium point back and forth. All right? Potential energy is a stored energy, and for a spring, with spring constant K and a displacement of x, we know that our potential energy is 1/2 the spring constant times the displacement squared. This is something we discussed when we discussed energy earlier. We have our spring constant units are newtons per meter, and displacement is meters. So what we have is our in the meter per second system, potential energy is max at the displacements, and 0 at the equilibrium position. For a mass with M and a height h above a reference line, we can determine that our potential energy due to gravity is mgh. All right, so we could use mgh in this system because we have a height from the equilibrium position. So the position from here to here is a height, and gravity pulls it down due to its mass, and that gives us mgh. Turns into kinetic energy, which is 1/2 mv squared. Once again, if you have potential energy turning into kinetic energy, you have mgh turning into 1/2 mv squared. You have mass on both sides of the equation, and they cancel each other out. All right, so we have for a pendulum, potential energy of gravity is maximum at the maximum displacement and minimum at the equilibrium position. All right, amplitude A is the maximum displacement from equilibrium in a frictionless system. Our amplitude is up and down or horizontal, left and right. How far below equilibrium or how far above equilibrium it goes, back and forth. And we'll see how this relates to periodic wave motion in a few sections. All right, so we have the amplitude is the displacement from equilibrium to the right or to the left. It is the displacement from equilibrium above or below. The time period it takes to oscillate up and down is not affected by the amplitude. So if I take a mass and do it just a little bit, it will, oops, if I do it, this guy up. If I take a mass and give it just a little displacement, its oscillations will be slow. If I give it a great displacement, its oscillations will be fast. All right? So the time period it takes to complete one cycle, whether there's only a little displacement or a great deal of displacement, whether there's a little amplitude or a great deal of amplitude, is not dependent on that amplitude. As we see here, the mass and the spring constant are what affect the time period in a mass spring system. All right? And we see here our energy in potential and kinetic energy taking place. All right? So we have our spring bouncing back and forth, and we see that in this system, as this goes up and down, we go from potential energy, elastic energy on top, and potential elastic energy at the bottom, going through equilibrium where there is no potential elastic energy, and we have a little kinetic energy at the very top and little kinetic energy at the very bottom, but it comes at its greatest point in the middle. So we have the solid line is the kinetic energy, and the dashed line is the potential energy. We start with a great deal of potential energy at the bottom. It's released, it goes to the equilibrium point, it goes past the equilibrium point. You have a great deal of potential energy at the top, and then it goes back and forth. We have kinetic energy, we have little to no kinetic energy at the bottom. It goes very fast, and then as it goes past the equilibrium, it starts to slow down, and then stops, and then goes back and forth and back and forth. At any given point, right, if we have half and half, we have a full total potential energy. So if we have all the kinetic energy, we have none of the potential energy. If we have all of the potential energy, we have none of the kinetic energy, and we have a ratio of our potential to kinetic energy equaling the total energy throughout the entire thing. All right, if you're watching this video on your computer at home, you can go to the website that I'm going to list right now, Colorado FET Simulations, and you can find the Hooke's Law demonstration here, where you can pick up masses and place them on strings, whether you know exactly what the masses are, or the Hooke's constant for the springs are, or whether you don't know these unknown ones. You can show the energy in the system as we discussed about. So we have the energy for spring number 1, And we could see as this oscillates, we could see the total energy in the system. And we have potential elastic energy, we have potential gravitational energy, and then we have kinetic energy over here. All right, we just saw simple harmonic motion with a mass on a spring system. And if we have a simple pendulum and we set it into simple harmonic motion, an angle less than 15 degrees will demonstrate the principles of simple harmonic motion when we want to solve equations. And some of these principles are that less than 15 degrees, we have a arc S displacement, or the total distance that the pendulum bob moves from equilibrium to its amplitude or farthest point. The amplitude is very close to this displacement x, which is the pendulum bob's displacement from equilibrium position at a right angle to the length of the pendulum here, L. So we see here that if we have an angle theta, which is less than 15 degrees, then we'll see that sine theta is equal to our x over L, our displacement from equilibrium divided by the length of the string that the pendulum's on. And now we can substitute this into determining the time period of a pendulum. We already knew that our restoring force, or when I pull this up, the force that restores it to equilibrium at this point is a component of mg. So the force that is drawing it back to equilibrium point is actually the sine of the angle component of mass times gravity. So knowing this, now we can substitute in for sine theta, we can put x over L, and we can determine that our restoring force for this pendulum bob to go back to equilibrium is mass times gravity, and instead of sine theta, we can have x, our displacement, horizontal displacement, over L, the length of the string. And we can also put this, knowing that we had Hooke's law, where Hooke's law says that our force is equal to the spring constant times the displacement. We can now substitute this into our equation where we had to find the time period of a mass on a spring. We had written that 2 times pi times the square root of m over k, the mass of the bob over the spring constant in the spring. We can now substitute our force, our restoring force, into Hooke's law constant, and we can determine that K is equal to mgx over L, and then divide both sides by x, and you end up with mg over L. You can substitute mg, mass times gravity, over the length of the pendulum bob into our equation right here. So take out the K and substitute in mass times gravity over the length. And let's rewrite this. So we have length over mass times gravity, and masses cancel out, and we end up with a time period that we can find which is 2 pi times the square root of the length of the pendulum times the acceleration due to gravity, 9.81 meters per second squared. And this is how we can find a time period for a pendulum that has an angle less than 15 degrees, so that our displacement, our horizontal displacement x, is very closely related to the arc distance s. All right, let's get this all erased. And let's go on here. We have our length, and we have our amplitude, which is the angle and the mass of the bob. We have energy of a simple pendulum in our system. Remember we talked about kinetic energy is energy of motion. So at this point, it's very near 0 in velocity. And at the opposite point, when I let it go, it's very near 0 at the highest point, or at the greatest displacement. But at the center point, in equilibrium position, it's at its greatest velocity, right? As it swings down, it increases in velocity at this point and then starts decreasing as it works against gravity. All right, and then our potential energy is just the opposite, where we have the greatest potential energy is its greatest displacement, and the least amount of potential energy is at its lowest point, and then once again it goes back up to the greatest displacement on the other side. And we see the same relationship between the energy in a pendulum bob as we just saw in a mass on a spring. And our total energy is the addition of kinetic and potential energy at all points. If you go to the Colorado FET site, you can do experiments using pendulums, and we could do it in real motion. We could have friction that slows the pendulum down as it loses thermal energy, or we can have a frictionless system where we do not lose thermal energy, and we can slow this down so that we can see that as our potential energy grows, our kinetic energy decreases. As our kinetic energy grows, our potential energy decreases. But our total energy is the sum of both of these bars at any given point. We add those two bars together, and you can see very easily that as kinetic energy grows, potential energy falls. As potential energy grows, kinetic energy falls. All right, so once again, we found the time period for a simple pendulum. Our equation is T equals 2 times pi, square root of the length over the acceleration due to gravity. And the period for time is independent of the mass and the amplitude, once again, as we see from our equation. So let's find the period of a pendulum is 5.2 seconds. Let's find the length of the string that holds the pendulum bob. So we have our equation, and we want to use algebra to rearrange our variables so that we can find length. And once again, what we do is we divide both sides by 2 pi, so we get t over 2 pi, and this cancels out. And then we square both of these, so we get t squared divided by 4 times pi squared. And then we have L over g, the length over the acceleration due to gravity. And then we solve out the g, acceleration due to gravity, multiply by both sides, and we get length is equal to g times t squared divided by 4 times pi squared. And now we plug in our numbers that we have, and our answer is 6.7 meters. The mass of the bob, what can we do to determine the mass of the bob? We don't have enough information to determine this. So we can't find the mass of the bob by just knowing the time of the pendulum swing.